Hey guys, hey, welcome to a lesson on combustion analysis. I'm going to go through the three problems that you have at the end of the notes. And if you have questions or whatever, you can come and see me individually if you need to, or message one of us and we'll see if we can get you some help. The AP tutors are excellent at this, So you can give them a shot as well. All right, so let's go ahead and get started. So what you're going to need are your notes and something to write with. You're also going to need a calculator. So you can kind of do these on your own. You really don't want me just going through the slides and doing them. You want to give them a shot. Combustion analysis are going to be the hardest problems that we do this unit, actually. And it's not that they're really difficult. It's that you have to kind of figure out where you're going. Let's go through and talk about them first. So what combustion analysis is you heat up a sample and you react it with oxygen. What to combust something means is to combine it with oxygen. So what we're going to do with combustion analysis is we're only going to use hydrocarbons or something that contains carbon, hydrogen, and possibly oxygen. In AP, we'll do it with amino acids and with nucleic acids, which also contain nitrogen. But we're not going to do that with you guys. But here, if you have something that has carbon and hydrogen, and it doesn't matter what numbers those are, what ratio it is, but when you add oxygen to it, that's a combustion problem. And what happens is they always produce CO2 and they produce H2O. All of the carbon from the original compound shows up in the CO2, and all of the hydrogen from the compound shows up as the hydrogen in water. Now, that's really important because if you know the masses of the two gases produced, the carbon dioxide and the water, you could use that to find out how many hydrogens or carbons in terms of mass were present in the original sample. And that's kind of the idea behind combustion analysis. And it's used all the time. Very easy way to determine what the empirical formulas are, and thus the molecular formulas of some of these hydrocarbon compounds, so organic compounds actually. So what we're going to do is I'm going to go through and do these with you, and I may kind of bounce around a little bit as it's been a while since I've made a video with you guys, but whatever. So it says here, complete combustion, reaction with oxygen of a sample of propane gas, and so we don't know how many carbons and hydrogens there are. So what we've got here is the same thing I wrote before. You've got something that has carbon and hydrogen combining with oxygen in combustion, and it is producing CO2 and is producing H2O. The amount of CO2 it's producing is 2.641 grams, and the amount of water is 1.442 grams. Now, in an empirical formula problem, you use your POEM, right? So percent to mass and mass to mole, divide by small, and round or multiply till whole. So what we're going to do is get to a point where we can actually do that. Now here we have carbon and we have hydrogen, but they're not in the forms of carbon and hydrogen. They're in the forms of carbon dioxide and water. So the easiest thing to do is here, take your carbon dioxide, which is 2.641 grams of CO2, and we're going to change this to either grams or moles of carbon. It's a lot easier to go to moles because when you do percent to mass and then you do mass to mole, well, if I have the mass of CO2 here, I can change from CO2 to just the number of moles of carbon in the original compound. So what I'm going to do is change from this to moles of the carbon. So the molar mass of carbon dioxide is 44.01 grams in 1 mole of CO2. In each mole of CO2, how many moles of carbon are there? Just 1 mole of carbon. At that point, I'll have the number of moles of carbon present in the CO2, which came from the original compound. I'll do the same thing for the water, but I'll of course change the water to the amount of moles of hydrogen. You could go all the way to grams here, and we'll do some other problems where we actually do have to go to grams, but in this case, you can stop at moles. But anyway, so 1.442 grams of water. The molar mass of water is 18.02. That's for 1 mole of H2O. And 1 mole of water has how many hydrogens? 2 moles of hydrogens, since it is H2O. So I'm going to do is multiply those out. This ends up being 0.06001. Now, this is going to be a ratio, so we're really not concerned with sig figs here. We're just, so you can use the entire number that you get as a result. And then down here, 0.1600 moles. Oh, I wrote that wrong. My mistake. Sorry, guys. You're probably shouting at the video. Moles of carbon, and then here, moles of hydrogen. So percent to mass, mass to mole. We have moles now. Divide by the smallest number of moles, which in this case is the 0.06001. And here I'll divide this also by 0.06001. And I'll get my numbers. The number for this one, of course, is 1. And the number for down here is 2.67. So the poem goes percent to mass, mass to mole, divide by small, and round till whole. It's really round or multiply till whole. If it's 2.99999, I agree you round. If it's 3.001, I agree you round. But if it's 2.67, then you really need to multiply it by something to get a whole number. In this case, if we multiply each of these by 3, multiply the 1 by 3 and the 2.67 by 3, you end up with a 3 for your carbons, and for your hydrogens, you end up with 8. This is actually the molecular formula, well, the empirical formula also, of propane. So you have to be careful. If it's really close to 2, then it's 2. If it's really close to 3, it's 3. But if it's somewhere in between, you need to multiply it by something in order to get that number. So here we go. That's propane. And actually, that is the correct formula for propane. This is the same stuff that is used in your gas grills, barbecue gas grills. So C3H8. Let's go do the next one. This one I may let you do a little bit more of it on your own. We'll see how it goes. Oh, what have I done? Oh, sorry, I left the answer in there for you to see. Okay, that's great. Yay. Okay, so this one is the second one, a little bit longer, but this one we don't have just a hydrocarbon. In other words, just carbon and hydrogen. I actually have carbon, hydrogen, and oxygen. I'll read it to you. You're going to isolate an acid from clover leaves, and you know it contains carbon, hydrogen, and oxygen. That's why I got CHO on the bottom. I don't know what these are. I'll call them X, Y, and Z. I don't know what they are. I am going to combust them under combustion analysis, and it's going to always produce carbon dioxide and water. So heating 0.513 grams of the acid. So what I'm starting with is 0.513 grams of that acid actually produces 0.501 grams of CO2 and 0.103 grams of H2O. So the carbon dioxide that's produced has all of the carbon in it, and the water that's produced has all of the hydrogen in it. But the original compound that I'm circling over there actually has carbon, hydrogen, and oxygen in it. So the way that we do this is the total mass of the compound, of the CHO compound, minus the mass of the carbon, minus the mass of the hydrogen, would equal the mass of your oxygen. Okay, and this is all mass down here. So whatever this mass is, which is 0.513, minus the grams of the carbon and the grams of the hydrogen will give you grams of just the oxygen. We're going to have to go actually and do that first before we do this problem as far as the empirical formula using our poem, is because we need the grams of every single thing, and we only right now have the grams of our total. We don't even have the grams of the carbon yet because we haven't done the dimensional analysis. So let's change our CO2 to grams of carbon, and let's change our water to grams of hydrogen, and then we'll do that subtraction I was talking about. Maybe it'll make a little bit more sense. So I've got 0.501 grams of CO2, and I have 0.103 grams of H2O. I'm going to change both of these into grams of the carbon and hydrogen. So this is 44.01 grams of CO2. It's 1 mole of CO2. 1 mole of CO2 is has 1 mole of carbon in it, right? And then what is the molar mass of carbon, or the atomic weight, if you like? It's 12.01 grams of carbon. That'll give us our mass of just the carbon that was in the CO2. And all of it came from that acid in the clover leaves at the beginning. All right. So let's do the same for water. Water's mass is still 18.01 grams of water is 1 mole. And then 1 mole of H2O has 2 moles of hydrogen in it. Now remember, this is hydrogen in a compound. It's not alone in the atmosphere where it would be diatomic. This is in a compound. So you're going to find out how many H's you have. So don't automatically give it a 2 subscript. That's silly. That's only hydrogen gas, or when hydrogen's alone. If it's in a compound, it'll have a different number. Could have a 2, but it more likely has a different number. So 2 moles of hydrogen. So 1 mole of hydrogen has a mass of 1.01 grams of hydrogen. And you can solve for those 2 masses. I'll just show you what they are for this one. And then I'll let you guys do the little part at the end here. So this ends up being 0.137 grams of carbon in the compound and 0.0115 grams of hydrogen in the compound. So that's what's in. These 2 things are what is in that circled amount. That means that if I take my 0.513 grams, it's actually going to equal, don't write this down, but it's going to equal the C plus the H plus the O, right? I already have my carbon and I have my hydrogen. I just did those. I need to go solve for the oxygen. So what I'm going to do is subtract those from the other side. So what I'm going to do here is I'm going to subtract, oops, here's the pen. Going to subtract my mass of my carbon and my mass of my hydrogen, 115 grams, and that will give me my mass of my oxygen, which in this case ends up being 0.365 grams. So now if you look over on the right, and let's see if I can underline them in a different color, that'd be lovely. So this one over here, this one over here, and this one over here are our masses of each of those things that we started with. So the poem goes percent to mass. Well, now we have the mass of all 3. Then it's mass to moles. So change mass to moles. And then divide by the smallest. And then round till whole or multiply depending on what you get. So why don't you see if you can push pause and go ahead and give that part a shot. Now you have the masses of each. Go ahead and do it as an empirical formula problem. And then I'll come back and we'll finish it up. Okay, so hopefully you did actually pause and not wait for me to start speaking again. That's bad. Shouldn't do that. But okay, so here I have all of my masses. I'm going to take my masses, change my color. I'm going to take my masses of each. So I've got 0.137 grams of carbon. I'm going to change that to moles of carbon. There are 12.01 grams of carbon and 1 mole of carbon. That will give me moles. I'm going to do the same for the hydrogen. 0.0115 grams of hydrogen. Zip, zip is 1.01 grams for every mole of hydrogen. And I'll do the same thing for my oxygen. 0.365 grams of oxygen. Zip, zip. 16.00 grams of oxygen is 1 mole of oxygen. And I'll get my masses for each of these, or my moles rather for each of these. So my carbon is 0.0114. My hydrogen is 0.0114, and my oxygen is 0.0228. Well, that's convenient. Look at those. So if I divide this by the smallest, which is 0.0114, divide this one also by 0.0114, and divide this by 0.0114, I get 1, 1, and 2. So my empirical formula for this guy is going to be CH02. So this was C, this was H, this was O, and I had 2 of the oxygens. So that's my empirical formula. They did ask me to solve for the molecular formula as well. They gave me we did this before, remember, it's the molecular mass or molecular formula weight divided by whatever your empirical formula's molar mass is or formula weight. You can call them the GFM and the EFM if you want, but it doesn't matter. It's the whole thing, the molecular compound's weight or mass divided by the empirical formula's weight or mass. In this case, the number they gave us was 90.04 grams per mole for the molar mass. And if I add these up, 12 and 1 and 32, you get approximately 45.02, which ends up being 2. So if you multiply that by 2, your actual molecular formula will be C2H2O4. O4. Ah, okay. O4. Sorry about that. It looks terrible. C2H2O4. Let me see if I can do that again. I think I have the ability. C2H2O4. Boop. There it is. Sorry about that. They're long problems. I'll give you that. Combustion analysis are kind of monsters in a lot of ways, but they're not too bad. This is kind of the only way they'll be asked of. I guess that's it. Asked of you. So if they give you one that has C, H, and O, you're going to have to do some subtraction to find out how much oxygen is present. Once you do that, you can then plug those 3 numbers, those 3 grams of carbon, hydrogen, and oxygen into a separate equation to find out your empirical formula. If they give you a molecular mass like they did, you could go and solve for what your molecular formula is as well. And so here's all the pretty work. It's done the same way pretty much as what I did. They did a little bit out of order, but that's okay. It's the same essentially. Okay, and this PowerPoint is online if you want to go back and look at it later. So this one is kind of a monster problem, the Dianabol. So Dianabol is an anabolic steroid. It can be used by athletes, of course, none at this high school. Studies indicate that the desired effects of the drug are minimal, and the side effects are actually quite substantial. So increased risk of sterility, liver cancer, heart disease. But people keep using it because it makes them bigger. They need to stop anyway, whatever. The molecular formula of Dianabol consists of carbon, hydrogen, and oxygen. It's an organic compound with oxygen in it as well. Can be determined using the data from 2 different experiments. So in one experiment, they're taking a certain amount of Dianabol and they're burning it. They're undergoing combustion analysis and finding out how much carbon dioxide and water are actually produced. So you could use those to find the mass of the carbon and hydrogen, just like we did in the previous example. The second experiment, they found what the molecular mass was. Fine, that means they're telling you the molar mass, so you can use it to find what the actual formula is rather than simply the empirical formula. So what I want you guys to do, I'll set you up just a little bit here, but I want you guys to try to do this one on your own. At least give it a shot. So they're telling you have a compound, Dianabol, that consists of XYZ. We don't know what those are. You're combining with oxygen in combustion analysis and producing carbon dioxide and water. What you're starting with is 14.765 grams of the compound. And what you're ending up with as CO2 is 43.257 grams, and the water is going to be 12.395 grams. So using that information, do the same thing we did on the last one. Change your grams of CO2 to carbon, your water to hydrogen, do some subtraction to find your O's and see if you can get the empirical formula for this, all right? So put the pause on, and then you guys go give this a shot, and then come back and watch me kind of speed through it a little bit. Okay, so hopefully you did actually push pause again. But anyway, so I've got my same thing here. I've got what I'm starting with. What I'm going to do is I need to know the amount of carbon, hydrogen, and oxygen. To do that, I'm going to have to find the amount of carbon in the CO2, hydrogen in the water, and then subtract from my 14.765 to find how much of it left over is actually the oxygen. All right, so let's start. 43.257 grams CO2. 4 grams CO2. Now, some of you may notice that there might be an easier way to do this. You know, it's just such a chemistry teacher thing to say, right? But actually, you could use a mass percent here. And I would expect my AP kids to do that. You guys, this is fine. The way you're doing it is totally right. It's no problem. But you could just do 12.01 grams over 44.01 grams and use a mass percent, which means you'd be multiplying times essentially the percent carbon in CO2 and get your answer. It'll save you some time. If you don't know what I'm saying, please don't do that. Do it this way. It's fine, but it'll save you a little bit of time. This gives me 11.80 grams of the carbon. Excuse me, I'm going to do the same thing with the water, so it's 12.395 grams of water. Water's mass is still 18.02. For every mole of water, there are 2 moles of hydrogen, and each mole of hydrogen has a mass of 1.01 grams. And so my hydrogen mass ends up being 1.39 grams of hydrogen in the compound. So what I'm going to do is take my total and subtract my carbon and my hydrogen. So 14.765, that's my total compound from up top. I'm circling it. And what I'm going to do is subtract the ones that I've got by. What am I doing? I'm not subtracting those. I'm subtracting these over here, the grams of each, to find the grams that are missing. So the grams of the oxygen. So minus 11.80 grams for the carbon, plus the 1.39 grams of the hydrogen. Okay. And what I end up getting from a mass of oxygen is 1.58 grams of oxygen in the compound. So I'll go ahead and box that. So those 3 right there are what I need to go and put in my empirical formula. And hopefully you were able to do that, and I am running out of space. Lovely. So 11.80 grams of carbon. I have 1.39 grams of hydrogen and 1.58 grams of oxygen. So I'm going to change each of these very smallly 2 moles. So it's 12.01 grams for every 1 mole of carbon. It is 1.01 grams of hydrogen for every 1 mole of hydrogen. This is carbon. This is carbon. Look at me. Just skipping steps. Sorry, guys. 16.00 grams of oxygen is 1 mole of oxygen. And I can go solve for each of those. What I end up getting for my carbon is 0.9825 moles. For my hydrogen, I get 1.38 moles. This is carbon, this is hydrogen. And for my oxygen, I get 0.0988 moles of oxygen. So I'm going to divide by the 0.0988 on all of these. 0.0988 and 0.0988 and 0.0988. And what I end up getting is 1, of course, for the oxygen. That's silly. I end up getting 10 for my carbons, and I end up getting 14 for my hydrogen. So my empirical formula, the simplest, is actually C10H14O. So that boxed one at the bottom is actually my empirical formula. The C10H14O. Now I'm going to erase some of this top part so I can do some of this other stuff here. So what I'm going to do is I'm going to take that empirical formula and calculate its mass. So it's 10 times 12.01 and 14 times 1.01. And oxygen, I have 1 of them, right? So that's 1 times 16.00. And I'm going to multiply all those and add them all together. And I end up getting 150.24 grams as my empirical formula mass. They told me that the molar mass was 300.44 grams. So if I do that little bit of math there, I end up with 2. So my molecular formula is twice the empirical formula. So it'll be C20H28O2. Boop. There you go. I agree. This dietable question was a monster. It's a little bit long. I'll show you the printed work down here, but it is in fact the same. A little bit out of order from the way I did it, but it's the same. And this would probably be a stretch to ask you guys a long problem like this, a difficult problem like this, but you should expect a combustion analysis problem for sure. So if it doesn't have oxygen in it, there's no need to do the subtraction. That'll save you some time. But if there is oxygen in the compound, you're going to have to actually subtract that from the original mass of the sample so that you can find out how much was present. All right, so that finishes up combustion analysis. Yeah. Oh, I have an extra page there. So yeah, let me stop this. So yeah, there you go. Ask us any questions that you have. I don't think our exam's for another week, or several days anyway. So we've got plenty of time to practice. See you guys at school.